Hello, my name is Zane Taylor, and I'm a rising senior studying materials science and chemistry at Caltech. I'm the president of our robotics team, and today I'm going to talk a little bit about hull design in the context of Gerald, our design phase submarine, which I helped design during this remote year. I have with me Lorenzo and Olivia, who will introduce themselves now and follow up this discussion with their own related work on Gerald.
I'm Lorenzo Shakewitz. I'm a rising junior at Caltech studying mechanical engineering, and I'm also on the mechanical team, where I've mostly been working on battery pods, an electronics package, and some manipulators. Today, I'm just going to talk to you about my work with the battery pod system and making it really easy to access and change during competition.
Hi, my name is Olivia Ernst, and I am a rising senior at Caltech studying mechanical engineering and aerospace. I'm on the mechanical sub team, and I've been working on simulations for pressure testing of the sub.
The hull of a submarine can be thought of as a foundation of a house. All other subsystems at all levels of importance are housed within or build off of that foundation. With this in mind, the hull must satisfy several competition and practical constraints. The entire submarine must weigh under 84 pounds in air to avoid penalty and have positive buoyancy by at least 0.5%, or half a pound for a maximum size submarine. The hull will take up much of this weight, and we would like it to provide a spacious interior for adequate electronics, easy access to that interior for debugging, and plenty of exterior space to attach critical systems such as manipulators or thrusters. But we must balance the pros and cons of such an interior with a safer and sometimes more utilitarian modular system. And of course, it must all be watertight. Many of these goals, however, are at cross purposes. More access to electronics means more leak points. Larger interior spaces result in more buoyancy, which must be counteracted by stronger thrusters or more mass, which pushes you against competition constraints. And conversely, modularity results in a greater mass to buoyancy ratio, which favors negative buoyancy and again pushes you against competition constraints. Modularity also introduces more need for system access, increasing the number of leak points while also making the pressure system more difficult to probe and debug, though it does offer more security since a single leak only endangers a single system rather than the whole submarine. Our long-term competition strategy is focused on fielding 2 submarines for tandem operation in the transdeck, each fully functional flagship designs able to support the full range of competition activities. Supporting 2 submarines at competition is directly rewarded by the competition rules, but also allows a team to attempt more of the tasks in a finite time and to specialize tasks if necessary. To fulfill this goal, we wish to fully phase out our eldest submarine, Flo, which was designed for solo operation, with Gerald, our design phase submarine, and our second submarine, designed for tandem operation. In addition, with Gerald, we wish to improve upon the design issues discovered in both Flo and our latest constructed submarine, Deb. With Flo, we had a limited exterior surface because of our curved dome, an unmodifiable hull because of her box geometry and construction, limited field of view with her fixed cameras, which also failed to achieve their objective of stereoscopy, and of course, difficult to access batteries. Deb addressed some of these issues, but not all, and introduced some new ones, such as a cramped interior space, limited useful exterior space, and again, inaccessible battery pods that Lorenzo will discuss in more detail. Deb did, however, discard the fixed stereoscopic cameras and replace them with a directable camera gimbal with a larger field of view. Learning from these issues and achievements, we designed Gerald with Flo and Deb's best qualities and introduced some improvements over both. By returning to the box geometry that Flo sports, we both simplify machining and increase the usable interior space. As you can see from these 2 images, while in principle the hulls might have similar interior space, Deb's cutouts, making the plus geometry, limit the utility of her space, leaving us with a less useful and more cramped interior. By returning to the box geometry and simultaneously increasing the size of Gerald, we lower the cost due to machining, attain a more useful and larger interior space, and also introduce a larger exterior surface on which manipulators can be mounted. This does, however, introduce some new material constraints as we begin to push the bounds of buoyancy and weight balance, which Olivia will discuss towards the end. Our first innovation unique to Gerald is the introduction of what we have called multiports, effectively holes in our hull that can be plated over when not in use, but which can later be easily modified to introduce new capabilities that we cannot yet foresee, such as pneumatics, unusual cabling, or, more interestingly, new sensors, like this downward-facing camera demonstrated here. This allows us to attain some of the greater flexibility inherent in modular design while retaining the simplicity of our box geometry. Regarding our main camera, we have taken a best of both worlds approach to combine 3D viewing through Flow's stereo camera and the larger field of view of Deb's gimbal camera to attain a flexible camera geometry with a more effective stereo camera system that can view objects in 3D at more useful ranges with a larger field of view. Now, I will hand off the discussion to Lorenzo to discuss his innovations.
Another major change with Gerald is the transition to a new battery pod system. So with Flow, we had this set of pink battery pods. They're pink in the picture. It's essentially an attachment to the bottom of the sub that the battery sits in. And to actually replace the batteries, you have to open up the sub, pull out the electronics, and then exchange the batteries, being careful not to drip water everywhere. That's a laborious process, especially when you're doing extensive testing. And so for Deb, we tried something new. We tried putting latches on the battery pods that are shown in lime green there. And while the latches were great in theory, in practice, they ended up being quite complicated because they had to be heavy and strong to hold the weight of the batteries. And they also had to, you also had to be really careful about water. You've got a sub covered in water and the water is dripping into the battery pod area. So you had to be really careful when replacing the batteries. So our major change in Gerald is to move the battery pods actually to the top of the sub. And these little nubs can't hold the whole battery. So most of the battery is inside of the sub. This is okay because we have a much larger sub this time. Basically what this allows is we have a removable lid on the top with a set of latches. You can just pull the latches out from the top of the sub right after you've pulled the sub out of the water, exchange the batteries super quickly. There's a lower brace at the bottom. There's a set of O-ring grooves. The reason we have that lid base is so that we can, so there's something to attach the latches to. And the lid base is secured with O-ring grooves. It does make for a more complicated watertight seal. But again, the big advantages of this new design are that we have very easy access to the batteries and efficient changing of the batteries. And also, as a little side effect of this, we have a lot more room for manipulators like torpedoes all throughout the bottom of the sub.
Pushing these limits of size, buoyancy, and mass has begun to introduce new concerns about material strength and hull thinness to reach appropriate buoyant forces, submarine mass, and resistance pressurization. Making sure the submarine can function safely requires more detailed and ongoing analysis that Olivia will now discuss.
The team has begun performing simulations to test the hull's ability to withstand a pressure of up to 10 psi, or about 10 meters underwater. This process was focused on ensuring that the hull's thickness, curves, and overall shape, including special areas designated for sectional cutouts, were able to satisfy the 10 psi loading condition. You can see these cutouts both on the sides, outside of the hull, as well as inside the hull. We suppressed many components of the full assembly to focus on the hull itself, since many pre-manufactured pieces that we buy from suppliers are rated for those pressures. These first two images show the top and side views of the hull assembly with an outside pressure directed inwards. We used 1060 aluminum alloy for the hull. The factor of safety for the higher stress green regions give us a value of about 1.5. These next images provide the same views, but for an inside pressure directed outwards. The factor of safety found is lower at about 1.2. To provide more context for these values, there are similar ongoing pressure testing simulations for the team's previous two RoboSub designs, Flow and Deb. These simulations are not yet complete since Gerald is still in the design phase. Given this additional information, the next steps for testing may include adding more ribbing to areas with stress concentrations to provide more support. The team is tasked with striking a balance between cutouts and ribbing. The first makes the robot weaker but provides more buoyancy, while the second makes the robot stronger but increases its mass.